All right, hello everyone. Welcome back to Machine Organization. A couple of announcements as we get started today. First, the worksheet from Lecture 9. My solutions had some errors in them. I apologize for that, and I'm going to totally blame having a fever when I wrote that. I'm still not feeling well. Sorry, this video is most likely going to be late, and is probably going to have a lot more editing than all the other ones as I chop out all the coughing that I do. In fact, we've got 2 students in our class who are currently hospitalized, so keep them in your thoughts also. With that in mind, the fact that COVID season is upon us, and we have our exam. The exam is scheduled for Friday. It'll be out Friday morning and available through Monday evening. If there are people who are still hospitalized at that time, I'm still going to allow them to take the exam when they recover. So please do not discuss any of the exam questions on Piazza. And I'll have more information coming about the exam as it gets closer. And last, there's a .vimrc file linked on the Canvas page under today's resources. This is not mine. One of the students submitted theirs, and I am very appreciative of it. It's a basic Vim file. Mine is actually quite complicated, and I don't think it's quite useful for students at this point. And in fact, I'm not even happy with it, and I have never made the time to go back and improve it. So let me jump over to a CSL machine and show you guys how this works for the .vimrc. It's just the configuration file for Vim. So what you want to do is cd into your home directory, that's cd tilde, and then if you list vimrc, you should see it's in here already. If you don't have one, you're using the defaults, but the first thing you want to do is make a backup of this. So copy vimrc to vimrc, backup, and then if you just take a look at it, you can see that mine has all kinds of stuff in there, including a lot of Chinese characters that I can't remember what they mean, and all sorts of configuration things that are set up to use extra plugins and add-ons. So the basic one is probably going to be a lot easier for you guys to understand. I'm going to leave that alone for right now. Okay, so the next thing I want to do is jump back over to PowerPoint and do just a little bit of review real quick. So what I want to look at is reviewing casting from one type to another. And the example I want to do is one of the more complicated ones. What I'm going to do is an example of casting a short to an unsigned integer. So this is going to go from a 2-byte, actually I think that's my next slide, yep. So it's going to go from a 2-byte short to a 4-byte int, going from a signed variable, and in fact we'll be choosing a negative number, to an unsigned variable. So I just want to show you what happens and what the result is when I do this. So the code for this would look something like this. I'm going to declare a short, assign it a value. I wanted to make sure there's a 1 in that very first position of byte 1 so that it's negative. So C is equivalent to 12 and is, let's see, 1100. So it starts with a 1. That's the only thing that matters. That's why I chose C. And negative 12345 is kind of a nice convenient number to check and make sure, and it's easy to remember. So the next thing we're going to do is we're just going to take that X, which is a short, cast it to unsigned, and this is a shortcut for unsigned integer. So the way I cast is just use parentheses followed by my variable. I'm going to store that into an unsigned int. As we do this, we're making 2 changes. So we're going to change from 2 bytes to 4 bytes and from signed to unsigned. So the question is, which comes first? Which comes first? And the order here matters. The answer is that the size is changed first. So to do this, remember we're going to be using sign extension. So it goes from CFC7. This begins with a 1. So we're going to add an extra 2 bytes of completely filled in with 1s to go from a short to an int. So in hexadecimal, that's just going to be adding 4 Fs to the front of this. And when you do this, if I compute this, I get a 42945,495 as the final answer. Oh, wait, I left a step out. After that, I need to convert from signed to unsigned. And when I do that, CFC7 does not do anything. It's still the same bit pattern. It's just how C is going to use that number in the end. And that's going to change depending on whether we're doing a comparison, like a less than, or I'm printing it out and telling it how to use that. Anyway, 42 billion something. So remember that changing the signedness doesn't change the binary representation. Only sign extension is going to do that when we go from small to larger. All right. So the next question I have is, I want to show you this is different. What if we had done this operation in reverse? If we did the sign first, that's not going to change anything. It's the same binary representation. So I still get CFC7, CFC7, but now this is going to be a positive number. And then when we, in fact, it's this number right here, when we go from 2 bytes to 4 bytes to make this the unsigned numbers, so the positive numbers take up more space. We just fill in with zeros. So instead of extending this with ones, we're just going to fill in with 16 extra zeros. And the final result is 53,000. All right, let me jump over to some code and actually show you this in code, how you could do this on your own. All right, guys, so I jumped over onto CSL machine. I'm going to fill in most of this in a second off camera, but just the highlights here. I'll be creating a short integer. X is equal to minus 1, 2, 3, 4, 5, so we got the -1. We'll be casting this to an unsigned integer. Unsigned int y is equal to, and then unsigned is the unsigned int is unsigned is just a shortcut for unsigned int. I don't actually need the int, and I'll be casting variable x to this unsigned integer, and then I'm going to print this out. Printf, let's see, print out x is equal to, we'll do it in decimal, and when I do this, I'll be looking at some big numbers. So I'm going to give myself a field of width 12, and this will just print this over on the right side of that field. So it's going to reserve 12 characters printed on the right side of that. Should be plenty of space. And then I'm going to print this out in hex also. So percent, I don't really care how big the field is here, it'll just use up the rest of the space. We'll go ahead, we'll put in 12 anyway. And the command for hexadecimal printing for a short is hx. I looked it up, it is there. I was really struggling to find this before. So S is for string, so S has already been used. H is the second letter in short. I think that's where this comes from. And then X is the symbol for, or the format code for hexadecimal. All right, so that should do it. And then we've got printing X twice. All right, looks good. Whoops. Whoops, oops, oops, oh, stop. Oh, let's redo. Is it R? There we go, okay. Copy, paste, there we go. Now I want to change all these and do the same thing for Y. So place that with Y. Place that with a Y, not that one, that's hexadecimal, not a Y. Y. Okay, there we go, that's what I'm looking at. I'm going to go ahead, fill in the rest of this so it's a real program, and be right back. All right, filled in the rest of this. Oh, I forgot return 0. And I made one mistake here. Right there under the cursor, I needed a U instead of a D to print this as an unsigned variable. All right, let's save and quit this. And then we will compile this. So GCC, we'll call it casting, whatever I call it, casting review. Get rid of that. That's the file, M32, all the warnings. And then I need this -O. Okay, now when I run this, casting review, here's what I got. X is equal to minus 1, 2, 3, 4, 5, exactly like I thought. Check this out. Printing as hexadecimal with only 4 letters worked. CFC7. I'm getting lowercase. Oh, I need the capital X in my code. I'll show you in a second where that goes. When I cast this, I do get a very different number from this one. Enormous number, in fact. And yeah, it's just prepended this with all of the ones there. So, oops, forgot to mute the volume. Casting view.c. Right here, I need these guys to be capital X. Now it should print as capital letters. Okay, I prefer that. That's the way I like it to look. All right, next up, I want to go back and show you the other demo where we're doing these in the reverse order. One sec. All right, so yeah, I just added a little bit of extra code here. So right here I'm declaring a short a equals minus 1, 2, 3, 4, 5, just like I had here. This is my equivalent of x. I'm going to be casting this unsigned short, or this short to an unsigned short b, and then we'll be casting the b to an unsigned integer and storing that in c. All right, and then when we print these out, I'm printing out the original one in both decimal and in hex as a short. This one's also a short, b, but it's all unsigned, so we'll be printing that out as unsigned. Then when we cast it to C, unsigned int, we'll be printing that out as unsigned and the full hexadecimal. But that won't matter, as you'll see in 1 second. Save and quit, and then I already compiled this. So when we print this out, we see that A is the same number, exactly as we got for X, exactly like I put in. When we cast this to an unsigned short first, though, it keeps the exact same bit pattern here. It doesn't prepend it with all of these ones, so no sign extension happens. It just decides how it's going to reinterpret the bits. It doesn't actually change any of them. Okay, and then the next thing we do is convert this from a 2-byte short to a 4-byte int, and that doesn't change this either. It's still the same bit pattern. It just adds a bunch of zeros here, which the printing function printf doesn't actually show. So it's been prepended with a bunch of zeros, and we get the exact same number. All right, so next up, I just want to talk a little bit about default casting when we do comparison. So if I have a comparison operator like the less than here, I need to have both sides, the left-hand side and the right-hand side, be of the same type in order to do this comparison. So this top one here, -1 is less than 0. That's obviously true, very easy. They're both integer literals because default value is for a number is integer. So that one will be true. Now, if I add this u here, that's going to say make this 0 an unsigned number. And so when I compare it to the -1 is less than an unsigned 0, this is a question. Which way do we do this conversion? It's automatically going to convert one of these numbers. And the answer is that it converts the -1 into an unsigned value. So it switches them to unsigned by default. And when I do that, this -1 becomes, as an integer, all ones. And this is going to be the maximum possible value of an unsigned integer when I do this cast. So it's going to be 1111111 is less than 0. That's obviously false when I do that. Let me demo this in code real quick. 1 sec. All right, so I put some of this into code below the line of slashes, which is a commented out row of slashes, which makes a great divider. I've created a new block. I'm using the brackets here for scope because as I was typing this, I just typed int b equals -1 less than 0. That'll take the result of this expression, and it returns a number, either 0 for false or 1 for true, and it'll store it in b. But I'd already used b up here, so that gave me a compiler error when I tested this. So rather than change the variables, I stuck this in curly braces, so now this b is a different b because it's in a different scope. That was just me being lazy. Sorry if that's confusing for anybody. Then I did the same thing, except I added the u here. So I'm storing the comparison between a -1 as an integer and 0 as an unsigned. And then I'm printing some stuff out. I just want to demo that this the -1, when it gets converted to the unsigned, printing that out as an unsigned and as the hexadecimal, and putting in -1u for both of those, is in fact a really ginormous number. And then I'm printing out b and c. So b is the result of this computation, c is the result of the unsigned version. Okay, so let's jump over here. We'll compile this, and then we'll run it. And I'll show you what we got. Okay, so this is the new stuff down here. -1u is in fact a really huge number, maximum possible integer, unsigned integer, and it's all F's. Sorry about that. I've still got my phone on because I'm expecting the results of my COVID test. They're going to call any second. All right. And then when I did this comparison for both as integers, -1 is in fact less than 0, so I get 1. And when I did the other version where I did -1 is less than 0 unsigned, this one came out false, even though it looks like it should have been true. So the moral of the story here is this is one of those little differences between that makes C special. And those are the kinds of things that are going to appear on the exam. Those little I guess they are a tricky thing. I don't intend them to be trick questions, but it's just something that you guys should be careful of as you're writing your own code. If you're doing comparisons between signed and unsigned, anything, it's going to convert them to unsigned, and you may end up with results that are unanticipated. The compiler will never tell you that's a problem. It knows exactly what to do. It trusts you as an expert programmer. So just be careful. All right, one last topic, just a small thing before we get into the Bitwise Operations, the core of today's lecture. And that is, how do we store multi-byte numbers in memory? So in the past several lectures, I've just been saying we have a 4-byte integer. I'm listing this as 0x1000 as the memory address, and then I'd have the next memory address as 1004. And ignore what's going on in the fact that this is actually 4 bytes of memory. So if I consider a 4-byte integer, 87654321, I've got the big numbers here as in the positions of the most significant bit, so I can remember that which way they go. But I have more than one choice when I store these in memory. So let's see here. This 87 will be a byte. Oh man, I said bit. I meant byte the whole time. Byte 3. The 65 will be byte 2. The 43 will be byte 1. And then the 21 will be byte 0. So I can either put them in with the 87 first. So I can go with byte 3210 with the most significant byte first. Or I could do it in the reverse order. So if I do the most significant byte first, it's going to look like this: 87, 65, 43, 21. This makes a lot of sense to most people. This is kind of how I've been writing it in the past when I've done some of these multi-byte examples where at the very beginning of the semester. But I have another choice too. I could put the least significant byte first. So I can put the 21 first, and then 43, 65, 87. And these are known as Endianness because I'm looking at the end of the multi-byte integer. Which end do I list first? The name actually comes from Gulliver's Travels. I'll put the little story up in a second. You guys can pause and read it. So I've got two choices. The big end first, big endian, means I'm going to put the most significant byte first. So the 87 in this case. And then I'm just going to list the others. The little endian, I'm putting the least significant byte, B0 here first. So 21, then 43, 65, and 87. And believe it or not, this is still today a huge controversy in computer science. It's been going on since the beginning of computer memory where we had multi-byte numbers. Which way do we store these? And about half the machines in the world, I'm using half very loosely, are big endian machines. And about half the machines out there are little endian machines. So you really... well, there's a pretty easy way to tell. I'll show you how to do that in a second. And with some code, you can do a little experiment. Let me throw up that story real quick before I dive into code. All right, guys, I got the story up here. This is taken directly from our textbook. It's from Gulliver's Travels. And I'm just going to go ahead and let you guys pause this. You can read it if you're interested. It is from our textbook. It was in the assigned reading. So if you've already read it, that's fabulous. But the original origin was about when you're opening up an egg, whether you are to break the small end of the egg, the little end, or the big end of the egg. All right, enjoy. All right, one more quick reason we might ever care about this before I jump into the code and show you how to figure out which machine you're working on. This is a really big deal because different computers use different systems for numbers. And so data transfer between computers, I'm going to send 1 byte at a time over the internet. So if I have a little endian computer that I'm starting and I'm uploading some information to computer 2, I need to know which way they've stored the bytes. So most of the internet infrastructure out there is big endian. So if I have a little endian machine, it needs to convert that to network transmission protocol, which is going to be big endian. And then because computer 2 here in my demo is already big endian, it doesn't need to do anything. It can just read the bytes in the correct order. We'll talk a little bit more about this in a future lecture, but one of the reasons we might care. All right, so I put together some code that's going to help us decide the endianness of the CSL machines. So just real quick, let me walk you through this. I've got my number here that I've been using in my PowerPoint example, 87654321. I'm storing that in num. Now, in 2 steps, the strategy I'm going to be looking at here is I'm going to take advantage of the fact that even though I've got a 4-byte integer, the character data type is only 1 byte. And so I can print out just 1 character at a time. And what I'm going to be doing is breaking this number into individual characters. So like 87 is going to be 1 byte. And I'm going to store that in a character variable. Well, I'm going to have a pointer to the 87 and the 65 and the 43 and the 21. So to do that, because num, C is already aware that num is an integer, I've got to do this in 2 steps. So I need to assign an integer pointer to the address of number. And then I'm going to take and cast that integer pointer to a character pointer. And now C is going to know that when it's looking at a character pointer, it only needs to take advantage of 1 byte at a time. Then I'm just going to print this out. I'm just going to go through 0 to 4. I'm going to pretend that this character pointer points to an array. And in fact, it does. It's pointing to an array of bytes here. I've got 4 bytes in a row. And I'm going to print those out. So the first thing I'm printing is actually the address of the pointer. So that's the P symbol, format character. And then I'm going to be printing out mem 0, mem 1, mem 2 for the different positions. And then the format string required to print out just 1 character in hex is, 1 byte is HHX. So I think what they did is they took the H from short and then just added an extra H. H might stand for half of that. I'm not really sure anymore. I couldn't find anything. But then I'm going to be just printing out the value, PCI, of whatever's stored in that. All right, so let's go run this code and see what we get. I already compiled it. I was testing a second ago. So when I run this, I see that I've got my memory addresses here. And they are, in fact, 1 memory location apart, C, D, E, F. It's not jumping from C to 0 and then to 4. It's jumping by 1 memory location. So I'm printing out sequential bytes. And then here's my memory array, 0, 1, 2, 3. And the values it's printing 21. So it looks like the least significant bit comes first at the lowest memory address. And then 43, 65, 87. So in fact, the CSL machines are little endian machines because the least significant byte, the 21 in this case, comes first. All right, and finally getting to the topic for today, bitwise operators. Okay, so in C, we've got 6 bitwise operators that I'm going to talk about right now. The first is the OR operator, and that's just going to be the vertical pipe. The AND operator, the ampersand. The NOT is the tilde. The exclusive OR is the caret, or shift 6. Does not mean exponentiation in C. We also have the left shift and right shift operators, which are just the double greater than or double less than signs. Okay, let's take a look at how these work. And I'm just going to go through this with some examples. First, we need all of our numbers to be in binary, so 1s and 0s. And then here's my example. So if I have X and Y, 1, 0, 1, 0, and I'm going to start with the top one. I'm looking at the OR operator. This is just going to take each of the pairs of bits in each position. So over here I've got the 0 in the B0 position and another 0 in the B0 position, and perform an OR operator on those bits and store that again in the resulting B0 position. So for an OR, if either one of these is a 1, it'll have a 1. Only if they're both 0 will it give me a 0. So in the B1 position, I've got 2 1s. That's going to be true, so we'll have a 1 there. Here we have a 1 in that position, so we'll get a 1. And here in B3, we have a 1 in the X variable, so that'll be 1 also. AND works exactly the same way. So in this case, instead of, if they're both 0, and we get 0, they have to both be 1 in order for this to be a 1. So both values must be true or 1, logical 1, in order to get a 1. So 0, 1 has a 0 right there, so that'll end up as 0. 1, 0 has a 0 here. So we're just looking at vertical columns in the same bit position. Now, how to just highlight here, I put in the numbers here. This is number 10, this is number 6. This resulting number really doesn't have a neat mathematical explanation at this point. To get there, really doesn't make sense. There's not a lot of connection. So here when we did the AND, we get a 2. The other one we got a 14. It's 14, right? Yep. All right, yeah. So not a lot of connection. So the next one is the not operator. So this is the only unary operator here. Wait, that's not true. Shifting is also, well, it only operates on one variable. All right, so this is the only real unary operator. So in this case, I've got my example 1010. When I do the not operator, that's just going to flip all of the bits. It's going to take ones and turns them into zeros, zeros turn them into ones. It's the same as the ones complement. So in this case, I've gone from 10 to 5. Again, no real connection here. If we were to add 1 to this, it would be like negating the number in 2's complement, because that's how the machines actually represent the numbers. Okay, next up, the exclusive OR. What we're looking at here, again, I'm taking two numbers. If the values in the positions are the same, that's going to return a 0. And there they are, they're both 1, they're the same, that's going to be a 0. And if they're different, so if I have a 0 and a 1 or a 1 and a 0, those are going to be return a 1. So it's going to fill in with a 1 in those bit positions. I'm trying to think of an example where that would be useful, and I know I've used it in the past, but my mind is blanking right now. Sorry, guys. Let me just move on. So the left shift operator is going to take a binary number and just move all of the bits over to the left. So if I'm doing a shift by 4, it'll take all the numbers, shift them over 4 positions, and give me the new number. So this 0 right here in B3 ended up in B7. The 0 here in B0 ended up in B4. So 0010 ended up 0010. And it's just going to shift in zeros for the bits that were vacated by the shift to the left. The most significant bits here on the left, because there's not room to store them, they are just lost. So we no longer have that data. All right, so pretty straightforward. It works the same for signed and unsigned numbers. I should also mention that the left shift and right shift are not strictly defined by the guidelines for writing C. They're compiler dependent or system dependent. And the guys who write the compilers can do whatever they want here. This is the most common way that we'll see this, and this is the way that it's implemented on the CSL machines. Okay, yeah, so right shift. This is going to depend on whether we have a signed number or an unsigned number. So, and whether, when we look at signed numbers, whether it's positive or negative. So the first example here, I've got a signed X. This is going to be a negative number. I can see because I have a 1 right there in the first position. If I were to do my right shift to the 4 position, that's going to take these 4 bits, the most significant bits, and they're going to become the 4 least significant bits. Because this is a negative, it's going to shift in 1s all the way across here. I'll talk a little bit about this as an example in just a second. For a positive number, like this number right here, it's going to shift in zeros. So the 0, 1, 1, 0, the 4 most significant bits become the 4 least significant bits, 0, 1, 1, 0, and it's going to shift in zeros. All right, this is known as an arithmetic shift. It's just the name of it. I can't for the life of me remember that. I don't expect you guys to either. Just happens to be what it's called. All right, so one way to think about this is we're going to be shifting in whatever's in this most significant bit position. We're just going to copy it over. My phone's been dinging all morning. It's a lot like sign extension. Okay, and then for unsigned values, we'll be using a logical shift. And again, I can't remember the name. I have to look it up every time, so I don't expect you guys to either. But here's the idea. Because we're looking at unsigned values, we're just always going to be shifting in zeros. So I take my 1001. These 4 most significant bits become the least significant bits. Oh, I didn't get this lined up very well. I'll fix that before I put them online. And we shift in zeros. All right, guys. So all of these bitwise operations are widely used and can be implemented to write some very efficient code. I want to just give you a couple of examples where this is definitely possible and places I've used them in the past. All right, so first up, I need to introduce the idea of bit masks. Bit masks are used to extract certain bits from a pattern. So, let me just do an example here. If I want to extract the 4 least significant bits from this number, if I've got x1001, 0010, I'm going to get just these 4 least significant bits, 0010. That's what I want. So to do that, actually, pause the video right here, go look at those 6 operations and see if you can figure out a way to turn 1001, 0010 into just the 4 least significant bits. All right, pause the video, see if you can figure it out, and then come right back. Okay, I'm back with the answer. It's pretty straightforward. We can use the AND operator to create a mask that'll clear some of the bits and retain others. So if I just look at this sort of bit pattern as a window, if I've got zeros here, it's going to block these because anything ANDed with a 0 is going to give me 0. So that's just going to cancel out all of these bits and turn them into zeros. And then if I look at the ones as if a window that I can see through, anything ANDed with 1 just stays what it is. So 0 and 1, when I AND it together, is going to give me the 0, again a 0, and this will retain the 1. So I'm going to end up with 0010, just like that. So that's all there is to it. Pretty straightforward. Let's do another example. So suppose instead of the 4 least significant bits, we want to get the 4 most significant bits. So I want to return, if I've got this number 1001, 0010, I want to return these 4 1001, but I want them to be in the least significant position here. So I just want to grab these. I want to know that my number is 9 in this case. All right, so pause the video, think about how you might do this, and I'll be right back with the answer. All right, guys, I'm back. Take a look at this. We're going to do this in 2 steps. The first thing we're going to do is shove all of these bits, the 1001, over into the least significant bit position. So they're in the right spot at least. So if we do this, this number happens to be a negative number. There's a 1 here, if it's signed, that is. So it will fill in the first 4 most significant bits with 1s when we do that. The 0010 is going to be lost because it's going to get shoved out of a place where there's no bit to store that data. And we'll get the 1001 in the correct position. The next thing we're going to do, step 2, is to use the AND operator to create that mask that's going to cancel out all these 1s I just shifted in and retain the 1001. All right. Pretty straightforward. I just had to do it in 2 steps. I'm going to jump down. Oh, yeah, there's the answer, 1001. Jump down. I want to talk about packed integers for a second. And here's my example. This is where it's very common. In computer graphics, we're going to represent colors by 4 numbers, red, green, blue, and then an alpha channel to represent transparency. Each one of these is going to be 1 byte, so it's got values between 0 and 255, or 0 to FF. And alpha is going to represent the transparency, so 0 alpha would be completely transparent. 255 or FF is going to be completely opaque. That means we can see it. This is used for compositing. If I want to layer images on top of one another, I can do that with alpha masking. Okay, so here's the idea. I'm going to store all 4 of these bytes, because they're just 1 byte, into a 4-byte integer, and it's going to save me a bunch of space. That way I don't have to waste a full int for each one of these numbers. All right, so the challenge then is, how do I get out a particular value? So if I want to grab blue, so it's going to be red will be the 8 most significant bits, then green will be the next 8, then blue will be the next 8, alpha will be the least significant. So what I really need, so alpha is going to be B0 through B7, blue will be 8 through 15, green will be, 16 to 23, and 24 to 31 for red. So if I want to grab a particular color, if I want blue, I need to be 8 through 15. Over here I was thinking, wow, I'm using green text. I shouldn't do blue as an example when I've got green text. And sorry to those of you guys who are colorblind, but here's the idea. I'm going to go ahead and grab bits 16 through 23 to extract the green color. And if in my green text here, I've got 0 red, there's full green, 0 blue, and it's fully opaque. I can totally see it. It's not transparent. So this is going to be my bit pattern for the packed integer for the full color. What I really want to do is extract just the green. It should be FF when I'm all done, or 255. So pause for a second, see if you can figure this one out on your own, and then come back for the answer. All right, welcome back. Here's the idea. We're going to do this in 2 steps also. The first thing we're going to do is shift this by 16 bits, and we're going to go to the right. So in this case, we're going to move, yeah, this is going to be 4 bits, 4 bits, 4 bits, 4 bits, and that's 16. So that will move this FF all the way over into the rightmost position. In this case, I'm starting with a leading 0 bit, so it's going to fill in with zeros. If this had been a 1, it would fill in with 1s. So once I get the FF over here in the rightmost position, the bottom 8 bits, I need to do a mask again, and I'm going to AND with 00000FF to just retain those bottom 8 bits. In this case, I didn't need to do that because it would shift in zeros, but I didn't know that. So I'm going to go ahead and do that anyway. All right, so there's the idea behind packed ints. Next up, I'm going to talk about bit flags a second, but I need to go make a slide for that. One sec. All right, I'm back. I made some slides for this. I'm pretty happy with them. So bit flags or bit fields are just a way that we can store Boolean data very efficiently. Boolean data is just a 1 or a 0 in C, true or false. I only need 1 bit for it. But C is going to use integers for that, so that's 4 bytes worth of data. I'm wasting all that space. If I wanted to, I could use a char and just only waste 7 bits. But here's the idea. If I have a lot of Boolean data to store, I can just use 1 bit for each piece and store that in an integer where I've got a whole bunch of these all lined up ready to go. So let's take a look at an example. Maybe this will make more sense. So here, I'm just going to declare a bunch of variables to use as my flags. So these are data that would, maybe represent a typical person. So they could be old or young. And I'm just going to store 1 shifted 0 positions into old. So that's going to be number 1. And then I'm going to keep track of whether they're employed or not. So again, I'm using Boolean data, true or false. So I'm going to take 1 and shift it by 1 position. And now I'll get 00010 or 2. And then for the rest of these, I'm a parent. I'm not married. I do not drive a Ferrari. Sorry, guys, this job does not pay that well. But then I'm just going to shift a 1 into whatever position. So this is my mask for each one of these different variables. So again, parent is going to be shifted by 2 positions into that spot. Married will be over here into that one. Drives Ferrari into the that position. Now here's the idea. Now I can create a variable that represents all of the data about me with just 1 statement. So I capitalized it. All right, never mind. Here's the idea. I'm going to create a variable Mike. I am 45 years old, so I'm older than a typical student. So we'll go with old here. I am employed. I've got a job where I teach this awesome class to you guys. And I am a parent. However, I'm not married and I do not drive a Ferrari. So I'm just going to list the things that are true for me. And that's going to shift a 1 into, I'm using the OR operator. So it's going to take these top 3 and OR them all together. So if I look at this, there's a 1 there. So that will be the B0 position will have a 1 in it. This will have a 1 in it. So the B1 position will have a 1. The top 3, there's a 1 there. So B2 will have a 1 in it. And then for the first 2 bits, B4 and B5, 0, 1, 2, 3 and 4, they are all zeros, so I'm going to get 0, 0. So 0, 0, 1, 1, 1 is a field that has all of this Boolean data talking about me. Now, if I want to use that, if I want to extract just one of these Boolean values from that, it's very straightforward, a single operation on the CPU. So if Mike and this is the bitwise old, this will give me, so the old field is right here, 0001. I'm going to AND with that 0001. So all of those zeros are going to cancel out all the rest of these bits. And then when I do old, that's going to have a 1 here. So this will return a 1. And anything that's positive is going to be true. So Mike and old says, wow, you're old. That will be true. If I use the drives Ferrari, I'm going to be ANDing with the 10000. So the 1 here is going to extract that 0, and I get 0. And the rest of the zeros mask out all of those. So in the end, that will result in a complete 0 for whatever is in my conditional when I use the bitwise and that'll be false. All right, so last up, I want to talk about multiplication and division. All right, now to wrap this up today, I just want to talk a little bit about a trick we can use to make multiplication and division go faster. So first, a little bit about speed. If I'm adding or subtracting, this happens very quickly on a CPU. 1 to 2 CPU cycles, depending on the architecture. I saw different measurements out there as I was looking up some data for you guys. However, multiplication is significantly slower. we're looking at 6 CPU cycles. So basically, multiplication is going to happen a lot like you learned back in elementary school doing the long multiplication. So I've got 32 bits multiplied by 32 bits. It's going to take each one of those rows, shift it over. I'm going to get basically 32 additions that I've got to do. They can do those in pairs, so it only ends up taking 6 CPU cycles to do that. There's some other technicalities here that can make this go much faster. Modern CPUs are pipelined, which means they can work on more than one multiplication problem at a time, and they can come up with an average throughput. If I've got lots of multiplications, like if I'm doing like a matrix multiplication or something, or I've got lots of numbers, or I'm doing it in a loop, it can do those more than one at a time and bring down this 6 on average to 1 on average. So this is a little bit of a trick. However, division tends to be very slow at 30 to 60 cycles. So this is a little trick we can use for multiplication and division by powers of 2, like 2, 4, 8, 16. Here's the idea. If I'm looking at multiplying 14 times 2, it's going to give me 28 in the end. 14 represented in binary, 1110. Okay, if I want to multiply that by 2, 28 in the end is going to be 0001100. Okay, so the idea is I'm just shifting these bits one position over to multiply by 2. And here's how this works. So if I write out 14 as the, what is this? The powers of 2 expansion. So I've got 2 raised to the 1, 2 raised to the 2, 2 raised to the 3. I'm adding all those together. So this will be 8 plus 4 plus 1 plus 2. Sorry, I misspoke. Plus 2. It's going to give me 14. And 28, when I write this out, 2 to the 4th, 2 to the 3rd, 2 to the 2nd. I add those up, I get 28. Hold on one second. Let me make another slide. Okay, here. I think this is maybe a little more clear. So I've got 14 times 2. Here's my binary or powers of 2 expansion of 14. When I multiply by 2, I can distribute this 2 into this summation here. So it's 2 to the 3rd times 2, 2 squared times 2, 2 times 2. And when I multiply something by 2, 2 times 2, that's just going to increase the power here from 3 to 4. So that's going to take that 3 to that 4 right there when I multiply by 2. And this is the exact same thing as shifting all of these bits to the left by 1. And it's going to be the same if I want to multiply by 4, I'm going to shift by 2 positions. If I want to multiply by 8, I'm going to shift by 3 positions. So just knowing this little trick, I can use this in my code anywhere I'm going to be dividing by 2 or multiplying by 2. Like if I'm doing a binary search or something, I'm going to be cutting my data set in half. I can use a bit shift operator there, and that's going to happen in 1 CPU cycle instead of this 30 to 60. Now in modern computers, they're very fast. You might never notice unless you're doing lots and lots and lots of division by 2 that I can get away from. But during the 70s, computers were not quite as quick as they are now. And this was an important trick. So you'll see this throughout older code. When you guys go get real jobs and you're looking at legacy code, you'll see this bit shift used for division all the time. All right, I think this is going to wrap it up for me. Yep, that was the last slide. Okay, so I'm going to go edit the video, put it together, and hopefully it'll be up before I have office hours. I'm running way behind schedule, so apologize for that. Hope everyone has a great day. Definitely stay safe and keep our sick classmates in your back of your mind. All right, have a great day.